Hi class, welcome to your first screencast. This is on chemistry. I want you to watch these videos, take notes on them with the note sheets that I give you or on your own, and I'm going to give you the bulk of the material. So make sure that you pause, rewind, and rewatch this as many times as you need to make sense. I'm only going to do the bulk of the material, so I'm going to kind of leave out some of the details so we could cover those in class. But I want us not to get behind, and with us doing the labs right now, we are going to get behind. So that's why I'm having you watch these on your own time outside of class. All right, so have your worksheet out in front of you with your periodic table, and let's get going and make sure we're going to do pretty much 90% of the front side today. All right, so the screencast is on atoms. Let's talk about chemistry and matter. Chemistry is pretty much the changes that matter undergoes. So all the changes that matter undergoes. And when we look at chemistry, we're really dealing with matter, because that's what the definition talks about, the changes that matter undergoes. Matter, if you remember from maybe a previous definition, matter is anything that has mass and takes up space, or has mass and volume, because taking up space is a volume. And there are three states of matter. There's solid, liquid, and gas. There's actually a fourth state as well that I'll talk about in just a second. So this first picture is showing a solid, and oops, let me get my pointer out over here real quick, and we'll do red. Okay. So this first picture is showing a solid. You can see that the molecules are all very close together, not a lot of space. That makes it a solid. When there's more space in between, it forms a liquid. It usually takes on the shape of the container. And then of course we have a gas that has no defined shape unless it is contained. But for the most part they are not. There's a fourth state of matter called plasma. Plasma is pretty much gas on steroids in a certain way, because it's when you have a gas and you shove it full with a lot more electrons, called ionization, and it reacts differently. It doesn't happen naturally on Earth very much, but 90%, more than 90%, 99% of the universe is made up of plasma as the main form of matter. Stars are made up of it. Lightning, you can find plasma in your plasma TVs, because it's also found in fluorescent lights and neon lights, and it makes aurora borealis and the northern and southern lights that occur every so often as well. So you can find it in different places. It's just not a major naturally occurring form on this planet. Okay, so let's talk about atoms, because atoms is really the basic unit of all matter. So when we break down matter, we get an atom. The word atom itself, A means unable or not. Tome means to cut. This is why we do the prefixes and suffixes in class. So unable to cut. And there's this guy named Democritus where he took something and cut in half, and then cut in half, and then cut in half, and then cut in half, and kept having it until he couldn't cut it anymore. The smallest possible particle that he could make, and he called it an atom. Now we know that that could now be cut into further things that we cannot see or cut ourselves, and we still call those atoms. But atoms, as we know now today, can be cut further down into something called subatomic particles. However, beryllium is an atom. Okay? And if you take this chunk of beryllium, it's made of lots and lots of beryllium atoms. The thing is that they all exhibit the same properties, which are listed below them. So I could take this whole chunk and they will have all these properties. If I take half of this chunk, it still has all those properties. If I just take a little chunk, it has all those properties. If I come over here and I just take one atom of beryllium, it still has all those properties. But this is where it differs. As soon as you go down to the subatomic particle and break it down into the particles, it doesn't have these characteristics anymore. It loses them. So that's why we call atom the basic unit of matter. Okay? Subatomic particles can't be, because they don't exhibit all the same properties. Now, we're going to talk about subatomic particles. These three different colored things are the subatomic particles. We have protons, neutrons, and electrons. We have protons and neutrons in the center part called the nucleus, not cell nucleus, atom nucleus. Nuke means center. And then we have these gray things which are on the outside. Those are the electrons. So let's look at them. Protons, you should have found out in your reading that they have a positive charge. Neutrons don't have a charge. They are neutral. Electrons have a negative charge. The mass of a proton is 1 AMU. The mass of a neutron is 1 AMU. And the mass of an electron is nothing. Okay. Now, what the heck is an AMU? An AMU stands for an atomic mass unit. An atomic mass unit is also known as a Dalton, named after the scientist John Dalton. And 1 AMU is the same thing as 1.66 times 10 to the negative 24th grams. So if you can imagine me drawing that 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 166 grams. That's how small it is. And now my hand hurts. So they're really small. Okay? And that's what 1 AMU stands for, this number right here. Okay? But nobody ever wants to use this number. That's why we designate it as an atomic mass unit. Now, right here, this is kind of a lie. Okay. Electrons do have a mass, but has more zeros out in front of it. It has like another 4 or 5 zeros out in front of it, which makes it even smaller. So it's so incredibly much smaller than protons and neutrons that we just say it's 0, even though it really does have a mass. It just doesn't really contribute to the mass of the atom. That's why we call it 0. The location of the proton is found in the center, called the nucleus, as are the neutrons. They're found in the center. They make up the nucleus. So when they stick together in the center, that forms the nucleus itself. People think that the nucleus is an object that contains them, that they're inside of, or that they're sticking to, but it's not. It's them clumping all together. The electrons are found in the orbits. The orbit is on the outside. It's also known as the electron cloud or the electron shells. And most of the time, people just draw orbits, sort of like planets going around the sun. It's not accurate, but it makes sense on why we would do that, so you could learn it. Now, some other information I want you to write down about protons is that the number of protons can never change, because it defines the atom. So if I look on the periodic table and I find that carbon has 6 protons, that's its number, 6. If I say 7, it's not carbon anymore, it's now nitrogen. So that can never change. Neutrons, the number of neutrons in an atom can change. And we will talk about this later. We call these things isotopes. Isotopes is when they have different masses. Electrons, the number can change. And when it does, we call it an ion. So this is when they get positive or negative charges. We will talk about ions later. This is important because it determines how the atom will react with other atoms. Sorry, my handwriting is so bad on this thing. But it determines how the atom will react with other atoms. It's the most important part, I think, of the atom, because without the electrons coming and going and trying to become stable, you wouldn't have any chemical reactions or form anything. Okay. So, this is what we call the nucleus. This is where the protons and neutrons are. That forms the mass, and the electrons are on the outside. Now, I have a stadium here. So I'm going to make an analogy. Atoms are really small, and it's hard for our brains to comprehend that. So let's blow it up to a gigundous size. Let's pretend that it's Cleveland Brown Stadium. So this one atom is Cleveland Brown Stadium. If you were to go to the Cleveland Brown Stadium and throw a peanut over here on the 50-yard line, a peanut, that peanut, in respects to the whole stadium, would be the size of the nucleus, which contains the protons and the electrons. That's how small. Then the electrons would be flies flying around the stadium. That's how small that they would be, and they're in constant motion, obviously. So most of the atom is actually empty space, and the electrons can move around. They don't have to stay in orbits. They're not confined to a certain orbit because of some gravitational pull. That's not how it works, like the solar system. They're allowed to move around in and out. But we use these orbits because electrons are usually found most of the time in a certain orbit. So if you go to the stadium and you have flies going around, they could fly anywhere, but most of the time they'll be by garbage, they'll be by food, and they'll be by the bathrooms. Doesn't mean that they have to be there. but most of the time that they are attracted to those areas. That's why we call it an orbit or a shell. The periodic table, we have to learn how to read this. There's a lot of numbers and there's a lot of organization to it. You will get most of that in chemistry, but let's just talk about what the numbers mean. So find your picture of carbon. The top number in the periodic table is the atomic number. This equals the number of protons. This tells you how many protons that the atom has. So carbon has 6. There's a symbol. It could be 1 or 2 letters. The second letter always has to be lowercase. Then there's a name, and then we have a number. Your number is rounded to 12, but the actual number is usually in a decimal form. To make life easier, we round it. That's the atomic mass. It's also known as a mass number, and it's also known as the atomic weight. The mass number is the number of protons plus the number of neutrons. These two things added up should equal this number. So I'm going to have you do a homework assignment that talks about figuring out the number of protons, electrons, and neutrons looking at a certain atom. So, if you're trying to figure out the number of protons in carbon, you look at the atomic number. There's 6. If you're trying to figure out the number of neutrons in carbon, you have to do a bit of math. You have to take the mass number, which is 12, and we know that it's protons and neutrons, and we already know protons. So if we subtract the number of protons, we should get the number of neutrons. So if this is the mass, we subtract the protons, there's the number of neutrons. So there is 6. So take the bottom number and subtract it from the top number. That will give you the number of neutrons. The electrons. The electrons always has to be the same as the number of protons. The negatives and the positives have to equal out because atoms have no charge. So if you have 6 negatives, you have to have 6 positives. So they are always the same. In this case, all 3 numbers are the same. That doesn't always work out. Usually neutrons does not have the same number as protons. Let's draw the atomic structure of carbon in your box. You could draw it like this, but there's an easier way. Instead of drawing all those circles in the center, we just shorthand it. There's protons in the center of the nucleus, and there are neutrons. These 2 numbers have to add up to the mass. So this is how I draw them. P plus for positive protons and neutrons, because they are neutral. Now we're going to put the electrons in. You could draw a solid line. I like the dotted line because they really don't exist. And the rule goes like this. The first orbit could only hold 2 electrons maximum. So we have 6. You could write E's, E negatives, and I do that sometimes. You could do dots with negatives in them, or you could just do solid dots, whatever you want. For this example, I'm going to do E's. So there's 2 electrons. Alright, but I have 6, and I just used 2. And if there's only 2 could fit, what do I do with the rest? Well, you make a new orbit around. Every orbit after the first one could hold a maximum of 8. Only the first one could hold 2. We call it the octet rule. Now, it's a bit of a lie. It's going to work differently in chemistry, but for our purposes in biology, the first orbit holds 2 max. Everything after holds a maximum of 8. So I have 6, I use 2, that means I have 4 left over. So 2, 3, 4 electrons. And that's what you have up here as well. This is what we call the atomic structure. And you're going to be drawing these, so get used to it. A lot of people prefer the dots. That's fine. Okay, here's a bunch of different ways that you could draw them. But you should always notice that the protons and the electrons are the same. So in this example of helium right here, the 2 protons, there are 2 electrons. In lithium, there are 3 protons, there are 3 electrons. And if you look at lithium and you add up the 3 protons and 3 neutrons, you should know that the mass is 7. So, again, lots of different ways to draw them. It's really a personal preference. Okay. One thing about atoms is that they are always neutral. So atoms are neutral. This means that they have no charge. So this means that the positive protons will always equal the negative electrons. This is important right here. The positive protons will equal the negative electrons. So for example, if I have 12 positive protons, I have to have 12 negative electrons. Just like in math, they cancel out. They are neutral, no charge. So looking at the periodic table, if we take titanium, here's the atomic number. That's the number of protons. So there's 22 protons. I know automatically that there's 22 electrons. Copper, there's 29 protons. There has to be 29 electrons. Nitrogen, there's 7 protons. There are 7 electrons. Last thing that we're going to talk about are valence electrons. Valence electrons are important. They are the outermost electrons. So they are in the outer shell electrons only. Okay. These are important because they determine how an atom will react with other atoms. So we need to know how many valence electrons there are. So let's look at these 4 examples. Here's hydrogen. The blue dots are the electrons. Don't worry about these white circles. Those are just vacancies that we will talk about later. So the blue are the electrons. So hydrogen only has 1 electron. So this is the outer shell then. It's also the inner shell. But it has 1 valence electron. Carbon's a little bit different. We have 2 on the inner shell. And we have 1, 2, 3, 4. So carbon has 4 valence electrons. We only care about the ones on the outermost shell. Nitrogen, how many does it have? 1, 2, 3, 4, 5 valence electrons. And then oxygen has 6 valence electrons. Now, valence electrons we represent in a symbol called an isotopic symbol. I'm sorry, not an isotopic symbol, a Lewis dot diagram. So let's look at, it's called the Lewis dot structure or the Lewis dot diagram, named after the guy, Lewis, who determined how to do this. So if we look at the valence electrons, hydrogen has 1. We need to represent that very quickly without drawing this whole thing, because this is a pain in the butt. So we do it by representing it with dots. So here's hydrogen, you draw the symbol, and then you draw dots around that symbol. So let me do a fake one up here. X is the element. This does not exist. This is a fake symbol. Now what you do, if it has 1 valence electron, you draw 1 dot. If it has 2 valence electrons, you draw 2. If it has 3, you go in kind of a clockwise or counterclockwise circular fashion. 4 electrons, you draw it like that. If it has 5 valence electrons, if it has 6, if it has 7, and if it has 8. Again, the octet rule, the most it could have is 8. The most dots that you could have is 8. And so you can see there could be 2 per side. It's like a box. Okay. So you're going to have 1 to 8 dots next to a symbol. So let's go back to hydrogen. 1 valence electron, 1 dot. I don't care what side you start on. Carbon, draw the symbol. It has 1, 2, 3, 4 valence electrons. So 1, 2, 3, 4. That's its Lewis dot structure. You should draw that one in the example box. Nitrogen has 5 valence electrons. 1, 2, 3, 4, 5. Oxygen has 6 valence electrons. 1, 2, 3, 4, 5, 6. In the end, I don't care where the dots go on what sides. Don't put more than 2 dots on a side of a symbol. That's the rule. So you could put them wherever you want. Typically they're done in a clockwise or counterclockwise fashion, but I really don't care. Those are called Lewis dot structures, and they represent valence electrons. And that will be important for later on. The last thing I want to go over is actually the periodic table set up so you know how many electrons, valence electrons there are. Anything in the first column has 1 valence electron all the way down. 2 valence electrons. These have different rules, which is why we don't show them. 3, 4, 5, 6, 7, and the most that an orbit could hold is 8. So you could actually look at the pattern that this periodic table is set up in, and that's an easy way to figure out how many valence electrons something has by just looking at what column it is on the periodic table. Last thing I want you to go over is isotopic symbols. Isotopic symbol is a simple way to figure out how heavy or what the mass of an atom is. So this is what you see on the table, but scientists like a shorthand method called an isotopic symbol. Isotopic symbols are when you write the symbol, carbon, and then instead you put the mass number as a superscript in front. So carbon has a mass of 12, so you would put 12 here. And then down here, as a subscript, you would put the atomic number. So 6 for carbon. This is the isotopic symbol for carbon that you should write down. If you do lithium, and you look at the periodic table, it's flopped. Lithium has a number 3, its mass is 7. So the isotopic symbol is lithium, 7, 3. Iron, its mass is 56, its atomic number is 26. Nitrogen, it's 14, its number is 7. It is reversed from what you see on the table. I know that's kind of a pain, but this is a quick-hand way. It's because carbon could have different masses, so some scientists work with carbon-14, which is radioactive carbon. You could do it for dating purposes. So they will write it like this. You need to know the difference between them. So this is just a quick-hand method, and it's called an isotopic symbol. All right. So next screencast, we're going to talk about ions and isotopes. The next one after that, we're going to talk about chemical bonds. I will obviously review this in class, answer any questions or confusions that you have, but I hope that this was helpful, and hopefully that you rewatch it if you need to. I'm going to also tell you other sites in case you could watch other videos to help you with this chemistry stuff as well. All right, well, I will see you in class, and hopefully you like this. See you later. Bye.